In this video, we're going to learn about net ionic equations. Now, until now, in this class, we've studied molecular equations, like this particular example here. They don't always explain really what's happening in a chemical reaction. So when looking back, we know that dissolved ionic compounds specifically, they dissociate from one another. They ionize, and you end up with these aqueous sodium ions and aqueous chloride ions, for example, when sodium chloride dissolves. So when I see NaCl aqueous on the left, I need to be thinking of there being completely separate ions from each other, sodium ions and chloride ions separately. And when I'm adding sodium chloride in aqueous solution to silver nitrate in aqueous solution, I should have a mixture of a whole bunch of sodium ions, chloride ions, silver ions, and nitrate ions that are floating around separately from each other. And actually, those will end up reacting, and we end up getting silver and chloride to stick together. But meanwhile, the sodium and the nitrate are just floating around. Again, since they're aqueous, they are separate from each other. So better than the molecular equation is the full ionic equation. What I'm going to do is show really what we have as reactants. We don't have sodium chloride floating around and silver nitrate floating around. We've got sodium ions, Na plus aqueous, plus Cl minus aqueous, plus silver plus, which is aqueous, plus NO3 nitrate minus, which is aqueous. And notice I'm adding these pluses to indicate these are separate species. They are not part of one molecule. They're all separate from each other. And it's important to, of course, know the charges, but this is really going in reverse from the formation of ionic compounds that you guys learned about quite some time ago. I know that sodium chloride is NaCl because I know sodium forms a positive ion and chloride forms a negative ion, and there should be 1-to-1. If we had a case of there being 2 of one ion, like for example BaCl2, that was aqueous, I would need to say that there's 2 Cl minuses in solution. That's how I would represent it. So I'd say Ba plus 2 aqueous plus 2 Cl minus is aqueous. That's how I would show BaCl2 being aqueous. Anyway, moving on to the other side, we know that silver chloride is a solid, so actually, since it's all sticking together, I show it like this. I don't separate it as separate ions, but with the sodium and nitrate, I do have to separate them. So Na plus aqueous plus NO3 minus aqueous. So the net ionic equation is an even greater simplification because when we look at the full ionic equation, what we find is that we haven't had the sodium or the nitrate change. I'm going to just put this in red. The sodium starts off positive and aqueous, and it ends up also positive and aqueous. So because this and this are the same thing, you can subtract them out from the equation and everything still holds. Same thing with the nitrate. What changes is, and I'm just going to underline this part in green, what changes is that our initial aqueous ions of silver and chloride become a solid silver chloride structure. So when I want to write what's called the net ionic equation, I cut through all the nonsense, all the stuff that isn't reacting, and I say that silver plus which is aqueous, plus chloride negative, which is aqueous, yields AgCl, which is solid. The sodiums and the nitrates are just spectator ions. These are called spectator ions. They are spectators. They watch as the reaction occurs, but they themselves do not participate in the reaction. And as I said, in the beaker, you're going to have some silver chloride precipitate out as a solid, but the sodium and the nitrate ions are just floating around freely. If you wanted, you could get sodium nitrate, but you would have to filter off the silver chloride, and then you'd have a solution of dissolved in water sodium and nitrate ions. You could evaporate off the water, and you would end up with solid sodium nitrate, but it would take a while to get there. So that works with double replacement reactions quite well. Double replacement reactions, you need to be looking for any case where there's a change in phase. So precipitation, where aqueous ions become solid, that works out well. Additionally, there are acid-base reactions where you end up with water as a product, and you have aqueous H3O plus and aqueous OH minus giving you water, as you'll see in chapter 14 and 15. So in those cases, you're going to have liquid water. Water is a molecular compound. It's liquid coming from ions. So that would be the net ionic equation there. Now here, we've got this molecular equation. Let's make it into a full ionic, and let's make it into a net ionic equation. Notice that we have, this should be F2 gas. This is going to be a single replacement reaction because we have a compound and a gas, and an elemental gas, I should say, forming a new compound and a new element. So what we can say is we have 2Na plus 2Cl minus, and both of these are aqueous, plus F2, which is a gas. They will form 2Na plus, which is aqueous, plus 2F minus, which are also aqueous, plus Cl2, which is a gas. And as I look at this, this is my full ionic. I look for spectator ions, things that have not changed. And well, my sodium ions have not changed. So I'm going to circle them. My sodium starts off positive and aqueous, ends up positive and aqueous. So forget them. But I do see that my chloride, I've got two of them to start with, and they're negative and aqueous. They become chlorine gas, which is neutral and gaseous. I start off with fluorine, F2 gas, which becomes F minus, that's aqueous, 2F minus, which is aqueous. So my spectators are the sodium ions. Everything else is participating in the reaction. So for my net ionic equation, I just write 2Cl minus, which are aqueous. I write, in addition to that, I say plus F2, which is a gas. That should be a 2. And they yield 2F minus, which is a gas, plus Cl2, which is a gas. And I spoke too fast. The F minus is not a gas, it's aqueous. Of course, ions will be aqueous. This is our net ionic equation, NIE, if you will. Great. So, I think it's pretty obvious what's going on here. This is a reaction that's a single replacement. But in the case of going back here, if I didn't give the precipitate, if I didn't clarify, oh, it's silver chloride that precipitates as a solid, how would you be able to tell? Like, if you only had sodium chloride, and you only had silver nitrate, and these were your reactants, if I said predict the products, you would have to predict what precipitates. And how would you know silver chloride is the one that precipitates and not sodium nitrate? Well, from here we have solubility rules. And if we look at this chart, which is badly copied, we can see that NH4 plus and NO3 minus will be soluble, and NH4 plus and ClO3 minus will be soluble. On the other hand, sulfate and calcium will not be soluble. So calcium sulfate, if that's the product of a reaction, then you would say no, that you would say that that's the precipitate, and you would be able to figure out your net ionic equation accordingly. So this chart can be very helpful to you. In general, all group 1 ions, all ammonium salts, all chlorate salts, perchlorates, all acetates, and all nitrates, they will be soluble. Notice, all ammoniums, they're all soluble. All sodiums, potassiums, none of these are shaded. And no nitrates, chlorates, perchlorates, or acetates are shaded. Beyond that, it's a little iffy, right? Like chloride, most chlorides are soluble until, wait, silver and dimercury and lead, lead 2. But I will say that the higher the product of the ion charges, the less likely something is to be soluble. For example, look at all these guys down here where they're insoluble. We have higher ion charges. There's nothing -2 around here. Or sorry, there's nothing -1 around here. They're all -2. Phosphate is missing from here, PO4 -3, and it is very much insoluble with almost anything, except for group 1s and ammonium. So down here, there are more things insoluble. Also, as we go to the right, we have more insoluble things as well, because as we're going further to the right, we're getting our +2s and our +3 ions. The +1s are over here. They tend to be soluble, unless they are larger. And that's another thing. The larger an ion is, like lead is huge, the more likely it is to be insoluble. Same thing with dimercury. Mercury is a very large ion. So that will help. I'll point out that if you ever are given something where, it says like ammonium nitrate and sodium chlorate are mixed together, write a net ionic equation for it, no combination of those 4 ions will give you a precipitate. So you would just say no reaction occurs, which is very much a possibility. Just because you mix 2 aqueous solutions of compounds together does not necessarily mean you'll get a chemical reaction. So you'll need to know your solubility rules, and this chart can be helpful. I may give you a different chart in class or some additional information as well. But in general, look for what precipitates, and that will be used for your net ionic equation. Anything else will be spectator ions. Hope this video has helped. Let me know if you have any questions or comments in the comment section below. Thanks.